And so I do not feel at all bad about telling you of the law of gravitation, because I am, in describing its history and the methods, the character of its discovery and its quality, talking about modern science.
Despite being one of the first forces to be discovered, gravity remains the least understood force even today. Physics has given us the liberty to predict the influence of gravity on bowling balls, stars, and planets with exquisite accuracy. Still, no one knows how the force interacts with minute particles or quanta. Even after almost a century, we stand right where we started, and the universe is doing everything in its power to make it even more difficult for us to understand whether gravity is quantum or not. For nearly a century, our quest has centered on uncovering a quantum gravity theory, an explanation of how gravity operates on the tiniest elements of the universe. This pursuit has been fueled by the straightforward notion that a single set of gravitational principles should apply universally, governing galaxies, quarks, and everything in between. Now, why is it important to prove that gravity is quantum? You see, 3 of the 4 fundamental forces of nature are described within the framework of quantum mechanics and quantum field theory: the electromagnetic interaction, the strong force, and the weak force. This leaves gravity as the only interaction that has not been fully accommodated. Quantizing gravity will be an essential step towards the path of a final theory, a theory that can answer all the phenomena in this universe. The observation that all fundamental forces, except gravity, have one or more known messenger particles leads researchers to believe that at least one must exist for gravity. This hypothetical particle is known as graviton. These particles act as a force particle similar to the photon of the electromagnetic interaction. The detection of gravitons would not only confirm the quantum nature of gravity, but also provide a means to scrutinize quantum gravity theories like string theory and loop quantum gravity. To embark on the exploration of whether gravity has quantum properties, it's essential to start from the basics. The journey to investigate the quantum nature of gravity was initiated by Freeman Dyson, a distinguished mathematician and physicist. Dyson posed a fundamental question: could the same conceptual approach that revealed electromagnetism as a quantum force be applied to gravity? The revelation of the quantum nature of electromagnetism played a pivotal role in triggering the quantum revolution. This insight originated from a mathematical technique employed by Max Planck to elucidate thermal radiation. Einstein, inspired by this approach, recognized the need to take the quantization of electromagnetism seriously, ultimately leading to his explanation of the photoelectric effect. Now, we understand that the electromagnetic field and electromagnetic waves, aka light, can be described as countless tiny and individual packets of energy called photons. Planck and Einstein's insights paved the way for the complete formulation of quantum mechanics in the mid-1920s. The theory of quantum electromagnetism, a precursor to the full quantization of electromagnetism, was established. Even before electromagnetism was entirely quantized, Niels Bohr and Bohr-Rosenfield presented a compelling argument asserting its fundamental quantum nature. If we take a look at the experiment, we might argue that gravity is quantum. Consider a moving quantum particle. At any given moment, the particle possesses both a position and a momentum. However, according to the principles of quantum mechanics, it becomes impossible to accurately measure both properties simultaneously. When precision in measuring position is sought, the uncertainty of momentum arises, and conversely. This fundamental aspect is called Heisenberg's Uncertainty Principal. The Heisenberg Uncertainty Principal serves as a fundamental constraint in our understanding of the quantum realm. Applying this principle to the electromagnetic field implies that if this field has a quantum nature, our endeavors to measure it will inevitably be subject to the inherent uncertainties defined by this principle. Now, instead of one, take 2 particles and give both of them a negative electric charge. Now, when we move these particles towards each other, then we know that like charges will repel, so these particles will interact with the electromagnetic field and be deflected back. We know what the uncertainty principle says, but we also know that the particle's motion is entirely defined by their interaction via the electromagnetic field. Bohr and Rosenfield argued that the restrictions on particle motion imposed by this principle should similarly apply to the electromagnetic field influencing that motion. And if that is true, then it's reasonable to think that the electromagnetic field is truly a quantum entity, which it is. If our ability to measure the gravitational field is limited to the interaction of massive particles, and these particles are influenced by quantum uncertainty, then gravity must be subject to the same quantum principles. Here, it's essential to pay attention to the details of the Bohr-Rosenfield argument. They realized in order to state that the Heisenberg Uncertainty Principal applies to electromagnetism, we need to focus solely on a pure electromagnetic interaction between the two particles. To understand the interaction, it must be influenced by the most quantum aspect of the electromagnetic field, often referred to as the quantum of action. This specific segment of the EM field being measured contributes to our uncertainty. Any additional components of the EM field would further complicate our ability to measure the field responsible for the interaction. However, electromagnetism poses its own complexities in this regard. For instance, as moving charges generate magnetic fields, these additional elements in the EM field complicate the direct comparison of our understanding of the EM field with the restricted knowledge that we have concerning particle motion in a pure interaction. So, can we show that electromagnetism also obeys the Heisenberg Uncertainty Principle? For that, Bohr and Rosenfield came up with a clever trick to clean up the EM field in their thought experiment. Instead of individual particles moving towards each other, they imagined pairs of particles, one positive and one negative, effectively neutralizing any emerging electromagnetic field resulting from the particle motion. This allows us to describe the most fundamental quantum interaction via the EM field. This enables us to demonstrate that the EM field is genuinely subject to true quantum uncertainty. However, when it comes to gravity, we encounter a challenge. Particles with electric charge experience the EM force, and the counterpart for gravity is mass. We can envision two particles approaching each other and interacting through quantum gravity. Our capacity to measure this gravitational interaction ought to be restricted by our ability to measure the motion of those particles. However, to establish that the limit is genuinely the Heisenberg limit, we need to rule out complex interactions for the gravitational field, just as we did for the EM field. So, why haven't we applied the same trick as Bohr and Rosenfield? We introduce opposing gravitational charges to each particle. However, this implies incorporating negative masses. As per our current understanding, negative masses do not exist, and exploring the fundamental possibility could potentially reshape our comprehension of the world around us. This means that Bohr and Rosenfield's logic cannot be applied to gravity, so what can we do about it? If we examine the next experiment, it begins to appear as though the universe is reluctant to unveil the secrets of quantum gravity. The most definitive proof of quantum gravity would be the identification of the graviton and its impact. Freeman Dyson outlined the requirements for detecting an individual graviton using a gravitational wave detector. They create ripples in the fabric of spacetime induced by massive objects engaged in specific types of motion. As they traverse, distances are altered. Space undergoes infinite stretching. At least, that's what the theory of relativity suggests. We know that electromagnetic waves are made up of individual photons, so if gravity is quantum, then a gravitational wave should be made up of gravitons. The Laser Interferometer Gravitational Wave Observatory made history in 2015 by detecting gravitational waves resulting from the collision of two black holes 1.3 billion years ago. The discovery was announced in 2016, confirming a major prediction of Albert Einstein's theory of general relativity. LIGO's observatories in Washington and Louisiana used laser interferometers to detect the space-time disturbance caused by the black hole collision, providing direct evidence for the existence of gravitational waves and validating Einstein's groundbreaking theory. So, what would it take to measure a single graviton? As of now, we're hoping to develop advanced tools in the future to detect that. But to estimate how many gravitons are in a wave, we can follow the steps used to count the number of photons in an EM wave. We take the total energy of the wave and divide it by the energy of a single photon. The typical gravitational wave detected by LIGO has an energy density of approximately 10⁻⁻⁴ J by m cube, with an angular frequency of 1 kHz. According to Dyson, the energy density of a single graviton in this frequency is at most 10 × 3⁻⁴ J by m cube, which gives us 3 times 10 raised to 37 gravitons per meter cube in these waves. So how can we detect a single graviton? Well, Dyson suggests that to achieve this, we need to be capable of detecting a change in distance at a scale of the Planck length. This requirement is actually independent of the frequency of the graviton. We know that Planck's length is the tiniest measurable distance. To measure changes on this minute scale in our simplified gravitational detector, we would require an incredibly precise instrument. This raises the question, what combination of masses and distances would be necessary for such a measurement? As a graviton passes our detector, the masses experience a minute movement. To detect this subtle change in distance, we must measure the positions of each mass with a precision equal to half of that change. However, the precision of our measurements is restricted by the Heisenberg Uncertainty Principal. As a mass is influenced by a graviton, its speed undergoes a change, roughly determined by the distance it covers divided by the time it takes for a single graviton to pass by. This time corresponds to the separation of the masses divided by the speed of light. Consequently, we obtain the variation in speed during our measurement. By multiplying this variation by the mass itself, we quantify the change in momentum resulting from the passage of a graviton. Having established the uncertainty in the position required to detect a graviton and the uncertainty in momentum induced by the motion of the masses influenced by the graviton, we can apply the Heisenberg Uncertainty Principal. This yields a relationship between the masses and the separation. The resulting equation provides the conditions necessary to detect a single graviton. The mass separation must be less than or equal to the gravitational constant multiplied by the mass of the masses divided by the speed of light squared. However, this expression is quite familiar and brings unfortunate news. It's the expression for the Schwarzschild radius. Any mass compressed to a size smaller than this radius is permanently trapped by its own gravitational field, resulting in the formation of a black hole. It is strange that we found that a gravitational wave detector capable of detecting a single graviton inevitably forms a black hole. That means even if it detects a graviton, it will swallow any information about that measurement, prohibiting us from confirming the graviton. Thus, it seems like the universe is not only prohibiting us from detecting quantum gravity, but also stopping us from making a gravitational detector. However, this doesn't mean the end of our quest to search for quantum gravity. Several proposals keep our hopes high, such as searching for the extremely rare interactions with particles of matter and gravitons, and to come up with a clean source of gravitons immensely more powerful than is currently known, such as a laser for gravitational waves. But there is also an indirect method. If we could use two particles to become quantum entangled through a gravitational interaction, then that interaction itself would have to be quantum, but this has not been achieved.